Good day, this is the presentation of our study, the design, modeling, and simulation of a wheeled wall press in-pipe inspection robot for pipes with 6 to 8 inches inside diameter. So, the background of the study, pipelines are necessary in transferring various fluids. However, a pipe's performance can worsen possibly due to cracks, aging, corrosion, and other physical damages. And to avoid such an occurrence, in-pipe inspection must be conducted consistently to check whether the pipes need to be maintained or replaced. In-pipe inspection is a task that can be challenging for humans alone to accomplish since there are pipes that have diameter so small that it would be impossible for humans to inspect the interior, which is why in-pipe inspection robots are being developed to make the in-pipe inspection easier, as the robots would be equipped with necessary equipment needed for its movement and data gathering. In testing, horizontal pipes are commonly used since the robot size doesn't need to match the actual diameter of the pipe. However, when it comes to vertical pipes, the challenge it is more challenging because the robot must climb the pipe while carrying its own weight at a certain speed to complete its task. In designing the pipe climbing robot for this study, uh, the authors have reviewed several literatures. Here are two authors that say that a wall press type is more advantageous in pipe climbing since it has a flexible mechanism and offers better traction. So the study involves mostly doing virtual prototyping, and we we found that from a study there are 5 steps. One, first is the modeling using CAD software, analysis through simulation, validation to check if the simulation model is an accurate representation of the physical model, refining if the simulation model is invalid, and optimization to improve the design of the simulation model. The study will mainly use Adams, and Adams is a software that tests virtual prototypes, such as robots, on a macroscopic level. The software incorporates real physics, and the simulation results can include the system's displacement, velocity, and reaction forces. Why? So, what is the significance of this study? So, based from a previous study done by Kagalpin et al., they've conducted a pipe. They've fabricated a pipe inspection robot. However, the design is only limited to 10 to 12 inches and horizontal pipes. The authors of those study have recommended that to create a pipe inspection robot that can climb vertical pipes and fit smaller pipe sizes, in which we the authors have done. And another significance of this study is the need for virtual prototyping before fabrication, because fabricating a robot like this may come as costly, and uh, virtual prototyping is a way wherein engineers can plan first on how to build their system, how to understand the system, so that when they will fabricate it, it will be less costly. As seen in the picture here in the presentation, here are the possible sources of failure analyzed by the authors of the previous study on why their robot cannot fit smaller pipe sizes less than 10 inches. So the specific objectives of this study are to design the improved pipe inspection robot design in Autodesk Fusion 360, to model and simulate the motor circuit of the robot to determine if the chosen components are operational, to create a simulation model based on the previous study to validate whether or not the virtual prototype to be made in Adams is accurate to the physical model, to determine if this study's improved design has stable motion by analyzing the displacement, velocity, spring force, and torque curves, and lastly, to evaluate the performance of the improved design by comparing the obtained data based on the change in pipe size and orientation. So here is the methodology. First, the researchers reviewed related literature, then designed their own pipe inspection robot based on what they read. Here are the selected components of the pipe inspection robot overall. And here's the design of the improved in-pipe inspection robot based on the chosen components. So what the important uh, the important materials to be obtained in this study are the spring and motor, which would be dependent on the weight of the robot. So here is the calculations in getting the spring. In getting the spring force, we would need that for our stress simulation test. Here's the calculation in selecting the proper motor for our robot. Next is the validation phase. This is necessary to check if the virtual prototype to be made in Adams uh, would be an accurate representation of the physical model. So that is why the researchers made a simulation model of the pipe inspection robot of the previous study. So they would make the robot based on the parameters given in their manuscript, as seen in the slide, and the mass would be either input through user input or by geometry or material type. The simulation model would include necessary constraints such as fixed joint to keep the objects still, revolutionary motion to allow rotational movement, spring damper to serve as the connector, and contact force to keep the solids in contact. So here is the simulation model that the researchers made based on the previous study. On the right is the simplified model. And for the motion simulation, the end time would be 3 seconds as done in the previous study, and the step size would be 0.001 seconds to better visualize higher frequencies of response. So here is the simulation done in as seen in the pictures, and the the results can be analyzed in post processor, wherein the curves can be analyzed alongside the animation to completely see where the where anything has gone wrong. For the circuit formation phase, we simply use the software to create the circuit and coded it and simulate it if it's working or not. For the motion simulation phase, it is similar to the validation phase, but only using this designs uh, only using this study's improved design of the pipe inspection robot. So here is the simulation model of our improved design. So next are the pipe settings. The researchers have decided to test the simulation model of the improved design in 6 pipe settings. First in horizontal pipes per pipe size, next in vertical pipes. So as seen in the pictures here and here, it is shown that the simulation model was able to climb vertical pipes, but we will see in the results on whether or not it is stable. So the following will be obtained in Allen's post processor as stated in the limitations: the total displacement, average velocity, spring force at each spring, and torque at each joint motion. For the overall torque, the torque values will be obtained first at each joint motion, then the sum of the 6 torque values at each time point will be obtained through the use of Microsoft Excel after exporting the data from Adams. So what we will analyze here is the robot stability through the curves and the performance of the robot through the change of characteristics based on pipe size or orientation changes. For the resultant discussion, so as seen here in the slide, through static stress simulation, whether the design experiences minimum or maximum compression from the spring force, there is no significant deformation. As well as here, using nonlinear static stress simulation using the maximum spring force. So the researchers have deemed that the design is acceptable as it would not experience significant deformation from the spring forces. So next, simulating the motor circuit in Tinkercad. So when the code was run in Tinkercad, the motors displayed an RPM of 143 RPM, but that is not the actual speed of the motor, but it shows that the circuit is working. So based on the simulation done in Tinkercad, the researchers can conclude that the chosen components for the motor circuit are operational. For the validation simulation based on the previous study, as seen in the slide on the curves, the robot was able to create an straight, almost smooth motion of its operation with slight shocks due to friction. And comparing the physical results and simulation results, there's only a small percentage of error, which can lead to the researchers concluding that that Adams is a valid method for creating virtual prototypes, which we would need for the improved design. So next, the results for the improved design. First, for the motion simulation. At first, the researchers have discovered that the torque had an extremely high value at 0 seconds, but we have discovered that the robot was not fully pressed into the pipe until 0.057 seconds. So that is why it was necessary to export the data after the simulation to convert to change the values to 0 at 0 seconds and disregard the data between 0 and 0.057 seconds. So after exporting the data, here are the curves. First, the displacement curves, where in all settings the robot was able to almost create a smooth motion inside the pipes, moving inside the pipes. It is also seen here in the velocity as well, with some small shocks. In the torque, there's some few shocks which should be explained in the analysis later. And here in the spring forces, as seen here in the spring forces here and in the vertical pipes, these follow a pattern-like curve. And from the analysis, the simulation model's motion is almost smooth based on the curves, and small shocks are seen in all four curves, which are due to the friction between the wheels and the pipe, the resistance from the spring forces, the slight rotation from the model from its initial position, gravity for the pipe climbing operation, adjacent springs that affect each other's movement, as seen why the spring forces have a pattern-like curves. And however, despite that, overall, the design of this study's improved in-pipe inspection robot is capable of having stable motion upon operation. So here are the changes in the characteristics when the pipe size or orientation changes. So as seen here, even when the pipe size or orientation changes, there is not much change that is significant to affect the robot's performance. So which is good, as any if the characteristics are large enough to affect the performance, the researchers cannot conclude that the design is better than the previous design. And seen here in the comparison of the old and new design, by comparing the values from the old design and the new design from the lowest obtained values, the researchers have concluded that the improved design has a faster operation time, which is good for fast pipe inspection operations. For the conclusion, the researchers have concluded that the robot the, the robot design in Autodesk Fusion 360, the improved in-pipe inspection robot design, experienced no deformation from the stress simulation, so which deems that the design is safe for operation. The motor circuit based on the chosen components were operational as well, which leads to the conclusion that the motor circuit based on the chosen components are correct. With less than 1% difference between the physical and simulation results, the use of Adams to simulate the virtual prototype of this study's improved design is considered valid. From the analysis of the four curves, it has been shown that the improved design can travel in horizontal and vertical pipes with stable motion. And from comparing the difference between the change in the four characteristics with based on pipe size or pipe orientation, there's not much significant change which affects the robust performance even when the pipe size or orientation changes. That is all. Thank you for listening.